Alright, these are the AP1 recorded notes for rotational dynamics, or torque. Torque is really just a force that causes rotation about an axis. And when we look at the formula, you'll notice it's very similar to linear work, except of how the actual force and displacement radius have to be orientated. Okay, so most all of you have done torque before. You already know something about it, because if you've pushed open a door or opened a cabinet or any of those types of things, then you have already done torque. Because pushing a door is an example of applying a force that then causes a rotation. Okay, for torque to occur, the pivot is in the hinge, and the force needed to cause it to rotate is dependent on a couple of things. One, for torque to happen, there has to be a force applied. Two, the angle of the force applied needs to be actually, there has to be an angle with which the force applied and to cause the rotation. There has to be at least a 90 degree. They can't be on the same plane with each other. So there has to be some sort of angle that exists between them. And then the distance from the pivot point will affect the torque as well. So torque's formula on the formula chart is torque equals the perpendicular force multiplied by the lever arm. So when you look at it, it looks like this. This is a lowercase tau in the Greek alphabet. And then you have your normal force, and then you have radius. Now this perpendicular sign actually is on the force. But as long as you either look at the distance that the radius is in the perpendicular or the force perpendicular, then you're going to be able to make torque work. But you've got to make sure that those two are perpendicular to each other. Okay? Now the units for torque are going to be Newton meters. So another way to think about that is a Newton meter is also a joule. So that's why I said it's kind of rotational work. That's not exactly true, but it's kind of a thought process for it. So the same torque can be produced by a large force with a short lever arm, or with a small force with a long lever arm. This is known as like a cheater bar when you have a wrench and you want to actually extend it. I actually have a special tire iron on my car so that I can loosen the bolts. But that's kind of, it is that I still have to apply the force. You want to apply it at a perpendicular angle, but you can get more. So you have torque with the first picture up here, just because there is force that's applied at an angle, but that force is shortened a little bit. It's actually a component of the overall force, and we have our radius here. This one, we're going to end up with even more force because the whole force is perpendicular to the radius. And this one, we're going to have the perpendicular force, but we're going to even have a longer radius. So we're going to have even more torque. So torque is dependent on the perpendicular force and the radius. So although the magnitudes of the applied forces are the same, the torques are different. Only the component of the force that's in the perpendicular to the lever arm will contribute to the torque. So let's go back to our door examples. So if the force is perpendicular like this, so here's my door, and this is the plane at the radius of the door, because all the rotation is going to happen from the hinge here. Then if the force is perpendicular to the lever arm, which we call R, is the distance from the force to the pivot, then you will have torque. Now here, I'm pushing on the door at its edge. So really this line of action is in line and it's parallel with the radius or the lever arm. And so if that's the case, then there's no rotation, so there's no torque. If you apply the force at some sort of an angle, so that we pull on the door at an angle instead of straight on, then the lever arm will be smaller, so the torque is actually less. And like I said, we could talk about it as if we wanted to look at this perpendicular force, then we would look at it as a component, and we would say that this is our component force along our radius, now that's perpendicular. But I could also look at it as now this is my radius, which is shorter, and this is still all of my applied force. So this would end up being a component of this. This right here would be the component of this, so that we would have our entire value here. So you can look at it as a triangle that way. But it is going to be less torque because you're looking at component pieces of it, not a direct force being applied at a perpendicular. So how can we use this information? Say the bolt's too tight. What can we do to get it to turn? Well, one, we can lengthen the radius. Like I said, add a cheater arm. Since this is being applied at an angle, the force is, we could apply it at a perpendicular instead of at a angle. So there's a couple of things that we could do to increase our torque, which would then help us loosen the bolt. So let's review equilibrium. We talked about equilibrium when we talked about forces, and we talked about static forces, where we talked about hanging pictures and things like that. So the conditions of equilibrium exist where the resultant of all the external forces is zero. So really we want our net force to be zero. So we've used this relationship to solve problems where the objects were stationary or at rest. As we said, all of the up forces or all the y forces in the up and down had to equal each other out, and then all the lefts and rights had to equal each other out. So the first condition of equilibrium was that translational equilibrium that we've already learned. It's when a body is in translational equilibrium. It's when all the vector sums of the forces acting on it are zero. So all of our x values are zero and all our y values are zero. So that's what we did to solve these types of problems when we did tension type problems in our free body diagram. So this had to equal this, and these two combined going up had to equal this one going down. So the second condition of equilibrium will be when an object is in rotational equilibrium. So that's going to be when all the sums of the forces and the torques acting on it are zero. So this is not only going to be that all our ups and our downs equal zero, and all our rights and our lefts equal zero, like the first condition for translational equilibrium, but the sum of our torques will also have to be zero. So we'll be able to talk about torque in a clockwise and in a counterclockwise direction, depending on which way the force would make it rotate. So for example, this picture right here, if this is the point of rotation right here, then if we pull on this, we're going to go counterclockwise. But if we pull on this, we're going to make it go clockwise. So this torque on this side will have to equal this torque on this side. So the sum will be zero. So that's where we can talk about the torques of counterclockwise and clockwise. So it's about which way it will rotate if you pull on that force value. Which way will it cause it to rotate? Okay? So let me move my little box here so we can look at it. So by choosing the axis of rotation, which is at the point of application of an unknown force, so like if I didn't know what this force going up was, if I took it out of the equation, then I'd be able to find some problems. So we'll talk about how we can choose that unknown force, and if we make it our rotation spot, we actually can take it out of the equation. So we will solve torque problems by using an idea of that counterclockwise torque balances clockwise torque when an object is in rotational equilibrium. So this is kind of what I was saying earlier in that previous picture of just everything that makes it go this way, torque-wise, has to equal everything making it go this way if we're going to keep it horizontally flat. So we will work on some problems in class, but until then, here's you a funny to leave with, and see you in class.